I am the director for the School of Computer Science, and I welcome you all to this third annual lecture on computer science and society. It's an event that is jointly organized by the School of Computer Science and the Carleton Computer Science Society. Before I introduce the speaker, we will have after the talk, we will have a question period. And after the question period, we will have, I've been told, hot pizza. So stay for a little social at the end. So today I'm pleased to welcome my colleague, Professor Alan Tsang. Professor Tsang is an assistant professor at the School of Computer Science. He has obtained his PhD at the University of Waterloo and was a postdoctoral researcher at the National University of Singapore. He conducts research on multi-agent systems, which analyzes systems populated by multiple reasoning agents, where the agents may be reasoning about each other. His focus is on the intersection between social networks and social choice. In particular, he is interested in how self-interested agents with bounded rationality interact with social choice mechanism and each other, resulting in complex emergent behaviors. Tonight, Professor Tsang will deliver a lecture on building a fairer democracy, a computational perspective. Please help me welcome Professor Tsang.
Okay, thank you very much for that warm welcome. I did note that I slightly changed the name of the talk when I was preparing it. I felt this was a better reflective of the actual contents. There will still be a lot of fairness in the talk, however. So we've already gone through the introduction, so you know a little bit about me. I grew up in Toronto. I was in Singapore for a bit. I do research, so some of you might know me from my ethics course, Computing, Society, and Ethics. My research area, however, as Michelle has said, is in multi-agent systems. And rather than sort of trying to define multi-agent systems, I thought I would sort of show you what it is throughout this talk. But first, I'm gonna fire up sort of official poll number 1. So let me give me a second to sort of fire this up. All right, so turn this on. All right, so today we'll be talking about democracy. So I thought we'd start off with a poll to see where we are. Right? How satisfied are we with the way that democracy is working in Canada today? We've done this in Canada specifically. So we'll let you sort of log that in, so you can scan the QR code or use this URL here and just type it into your phone or whatever other devices that you have. Right. So it's been kind of a tough few years for sort of democracies around the world. Right. We've had sort of this very divisive elections in the U.S. Right, south of us. We've seen the election of populist and authoritarian figures all around the world. And of course, we've seen the storming of the US Capitol, and sort of closer to home, we've also had the convoy protest, the Freedom Convoy here in Ottawa. And so to put things into perspective, for a while, right, for the last couple of decades, democracies were on the rise, right? It seemed like democracy was the way to go. The world's richest economies, most well-developed countries were all democracies. But it's important to note that historically, that's not been true. Right? So here we have this is a chart that I pulled off Our World in Data. They have the actual citation from the data there, and it lists sort of like this diagram of what kind of governance are exercised around the world. Right? And we can see by year. On the left, the data goes back to 1789 to 2022. How many of the world's governments were democracies, right? electoral democracies or liberal democracies are sort of in blue, whereas more authoritarian regimes are sort of in red and orange. And we see that while recently, maybe a slim majority are in democracies, historically that's not been true. Historically, democracies are a very rare form of government, and it hasn't been around for very much. And keep in mind, this diagram goes back to 1789. Presumably that was as far back as they were able to get comprehensive data on. But of course, we could go back, we could fill in the rest of this diagram to recorded history, right, to the fall of the Roman Empire. This would go, this was to scale, right, if we're talking about recorded history, this would go probably to the next building over, almost entirely in red, maybe with a thin sliver of orange, maybe a little bit of blue here and there. So democracies are historically rare, and it's difficult to achieve, right? And in sort of recent years, we've seen this increased dissatisfaction in democracies. Here we have around the world, right? So we have on the x-axis time again. On the y-axis, we have how are people satisfied with the way the democracies are. This one is across the world. This is from UK-based reports. And we see that in the last sort of decade, dissatisfaction has been trending up. Right? And this has been across the world. This is in Anglo-Saxon countries, right? So UK, US, Canada, Australia, and New Zealand are the main ones, I think. And here we see a much starker trend in recent years. Again, the dissatisfaction with democracy is trending upwards. And here we have a breakdown, right? So here we have a breakdown by countries. Canada here is sort of in the middle. Again, higher up means worse. Right? So we do have this positive trend towards increased dissatisfaction in recent years. How do we compare in this room? So here we have, as of 2020, the increase has been, this is, I can't quite read it off of this. This is basically measuring the delta, right? This is the rate of change. But if we go back to the previous one, across Anglo-Saxon countries, satisfaction's around 50% as of around 2020. And so here we have the our poll here. Okay. All right, so that's our result here, almost spot on. Right, so we people that agree that we are completely satisfied, it's about 54%. Yeah, so about 50%. So we are not a representative sample by any means, but certainly the average is spot on. Right? So this idea that it's a fairly big problem, right? That we're having that faith in democracies is decreasing. What can we do about it as computer scientists? So in this talk, we'll talk about what is it that we can do about it as computer scientists. Obviously, the problem is very big, as we'll see in a moment. We can only sort of tackle specific aspects of it. So we'll talk about a model for how voting occurs, or a theoretical model of different kinds of voting. And then we'll talk about a particular way of approaching a problem that's faced in governments around the world, how to divide resources fairly. And we'll wrap up with maybe a little bit about information propagation, how information moves and affects our decision making, very, very briefly, and maybe a few other projects. So, talk about what is voting, right? It's this core part of the democratic process. What exactly is voting? Well, it's a process by which a population, a group of people, collectively make decisions. And there are multiple parts of this that are important, right? So we have a population of people that are voting, right, that are involved with this decision-making process. They make a decision together that is binding, right? The result that they choose is enforced on the population, right? It's not a kind of a fake result. It's a result that really matters and affects the happiness of the individuals. And therefore, all of their opinions should count in some way. That they should factor into how this decision is made. And that gives us sort of a framework of what voting looks like. And this should not be strange to anyone, right? If you voted, then you know that there are voters. Voters get turned into ballots, or the voters submit ballots, and then the ballots are aggregated together to make a choice. And so is there some way of modeling how voting occurs? So this is a very simple model of voting. Suppose that the voters, right, the people that are involved in this community that want to vote, are trying to choose the best outcome for a particular problem, and the best approach to a particular problem, the best answer, and that such a best answer actually exists, right? That there is some correct, objectively correct choice and an objectively incorrect choice. Now, let's say there are two choices for the sake of simplicity, but we don't know which one, of course, is correct and which one is not correct, right? We could say that the world exists in one of two states. We'll call this the ground truth. We don't know which state it exists in, but it does exist in one of those states, right? One of them is right and the other one is wrong. It's a very, very strong assumption to make, right? And that definitely does not apply to maybe when we think of voting, most things that actually you vote upon. And each voter has some private noisy signal that they're privy to, right? Some private special information about the state of the world, about the ground truth, and they will submit a ballot based on that state. You could think of some secret information that they have access to, some insight or some knowledge, some expertise they can use to evaluate what the ground state. It's not a true coin flip for them, it's a slightly biased coin flip. Right? And then so they would cast a ballot according to that state, and then there would be some process for aggregating those ballots. You might think that that's kind of a strange assumption to make, but we actually just did it, right? So the poll that I put up on the intro slide, that very first one, that is epistemic voting. The world exists in one of those states, and we don't know which one it is. So these two icons, I heard some people, they don't know what these icons, I didn't know what they are either. So this is our Ottawa Senators, it's our hockey team. They're playing the Seattle Kraken, which tonight, in 4 hours. The world exists in one of these two states where either one of these, or maybe there's a tie, right? Either one of these will beat the other, right? There will be a winner or a tie in this hockey game. And that is for certain indisputably true, right? That is a fact of the world. The world will be in one of these two states. And so if we were, as a group, trying to select the correct answer, right? Who will be the winner of this hockey game? Well, there is a correct answer and there's an incorrect answer. Each voter might have some idea of what the likely outcome is, but this is, as far as I know, there are no time travelers or no one with oracular powers in this room. If you do, let me know. We'll do something. We'll make some money together. So this signal is very noisy, right? We might have some of us might follow this more closely than others, right? Have more expertise on what's happening in the hockey world, right? Who traded whom, who got injured, right? So some of us might have a stronger signals than others. And so we've been voting with these sort of noisy signals, and it's time to aggregate those ballots. Let's see what those ballots turn out to be. Right? So here we have poll number 0, right? So we said 3-2. We think that the Senators will at least tie or win outright. Right? So that's the result, right? We've aggregated those results, and in 4 hours' time, we'll see if that result is correct. And is there some degree of conviction that would be correct? We didn't see that many people vote. We're just that point in the moment. But there is, if we had enough people voting, we might expect that we should be able to get the right answer, right? If we had enough people. And this leads to this idea of the wisdom of the crowds, right? So this is an actual observation from a scientist of sorts, certainly a philosophical thinker, who went to a county fair, and there was this task, this kind of game, right, that they played at the county fair, where you have a cattle, right? I think it was an ox, and the participants are invited to guess, probably for a prize, what the actual weight of this ox was. Right? And so your task is to guess the weight of this ox. And what he observed was that if you took all of these guesses and wrote them down and then took their mean, it's actually more accurate than any of these so-called experts that were guessing the weight of this cow, right? Whether this actually happened, actually, he wrote it down, so he alleged that it happened. Whether this actually happened or not, it's like Sir Isaac Newton's apple, right? You can think of it as a thought experiment, but this idea of the wisdom of the crowds, if everyone receives a noisy signal, we can aggregate those noisy signals and choose the correct answer. And this, right, this actually is a central theorem of computational social choice, what's called Condorcet's jury theorem. The task is to predict, so let's say the winner of a hockey game. We aggregate all these signals. If we make the assumption that each of the voters, or at least the average voter, is correct at least half the time, right? There's only two choices. So the worst you could be is you flip the coin and you pick that answer. And your rate of guessing that answer is exactly 0.5. If we assume that the voters have some small probability greater than 0.5 of guessing the answers, right? You only have to be slightly better than guessing. Then if we have enough voters, and we also assumed independence, right? Modulo which team is actually stronger or more likely to win. If these roles are done independently, then if we aggregated all these answers, if you have enough voters, the probability of guessing the correct answer in aggregate goes to 1. Right? And this is Condorcet's jury theorem. You could prove this yourself. It's the binomial distribution. Right? You can think of these as like Bernoulli trials. You could plot the graph. This is from Wikipedia. Right? As the competence of the voters grow towards the right, you would think of starting off at 50%, right? As you move towards the right. If you have one voter, well, then your probability of guessing correctly just increases linearly as the knowledge grows. But if you have as many as, let's say, 12 voters, or we have maybe 20 people in this room, 25 people in this room, so we're above this line, right? So we would see that as our competence grows, the average competence grows, the probability of getting an answer increases quite quickly. Right? And this is the gist of what's called the jury theorem. The jury theorem is sort of framed in the context of a jury of your peers, right, at a trial, whether they would be able to find the correct answer, right? There is an epistemologically correct answer. Epistemology means nature of knowledge. Right? They would be able to uncover whether this person on trial was guilty or not, right? This is one of two options, and there is some correct answer and there is an incorrect answer. And he said, if the voters are at least more competent than flipping a coin, right, which hopefully they would be, and they made this assessment independently, modulo the actual ground state of the world, whether this person was guilty or not, that if you had a larger number of jurors, that you would be able to arrive at the correct answer more often. We'll find out in about 4 hours' time whether n was sufficient. We have n equals 5 basically for this experiment, so we're actually closer to this green curve. So we'll see. So another question we might ask is, what if I let you converse with your peers? So some people here didn't know what either of those teams were, and so maybe you were closer to the coin flip. Maybe some of you are real experts. If you were to allow to talk to each other, we might think that this would help the process, or maybe it would hinder the process. Right? So your ballots would no longer be independent because you've talked to each other, you've correlated your ballots together. Right? But we might believe that, again, this is under epistemic voting, right? There is some true state of the world that the correct choice would have a better chance of being arrived at in a conversation than the incorrect choice, right? All else being equal, right? If we're making this epistemic voting assumption that there is some actual correct choice that could be chosen. Right? And this leads to one of my earlier papers, actually. Should social network structures be taken into account in elections? A very kind of inflammatory question on the surface, but if you're allowed to make this epistemic voting assumption that we really are trying to work together to uncover what the true state of the world is, what the correct solution is, what the correct choice is, then maybe this is like slightly more acceptable, or we're not looking into your social networks to like censor people. We're trying to just find the correct answer more frequently. And so we were able to answer this question in the affirmative by making this assumption that it is easier to convince someone of the truth than of a falsehood. Right? And that seems like a reasonable assumption to make. This was written, the writing of this, the nucleus of this idea came before 2016. So afterwards, maybe this is a little idealistic. Right? So the corollary is that if you looked at the graph, one of the things you find is that once people have had a conversation, the correct result would, if you looked at pairs of friends that talk to each other, the correct result would be agreed upon more often than the incorrect result. And it comes out of a corollary of this assumption. And there's quite a bit more math that goes on under the hood. We use a maximum likelihood estimator, but we're able to construct an algorithm that looks at a sort of interaction network, right? A social network. After conversations have taken place, people submit their ballots, and we're able to actually identify the correct state more often than a naive direct vote, and than if they just directly cast their ballot, which was kind of interesting. And you can see like the plot here, right? Wow, our model is the solid blue line. The naive voting is, or direct voting is the dashed red line. So that is epistemic voting, right? We assume that the world is in one of two states and we're trying to guess the correct state. Now, frequently, this is not the case. And usually when you think of voting, right, as a political context, maybe we don't think of there being like a correct state. Maybe you do. But certainly there is room for there to be this idea that, well, maybe it's not subjective, or sorry, it's not objective, it is subjective, right? We've just talked about pizza, right? Should pineapple be on pizza? And rather than putting that poll, which might lead to a great deal of disagreement in the room, we'll put up something slightly less inflammatory, right? So we'll put this one up here now. All right, so what is your favorite movie amongst the choices here, right, to watch at the next movie night, right? And so you can take your pick, right? Which one? We've got Contagion, we've got Rogue One, Arrival, Transformers, Blade Runner, the new one. You can make that choice. This captures the idea of subjective voting, right? We really are subjective preference. There's no correct answer, right? Though some of you might insist on one or the other, but deciding what movie to watch together is a subjective preference. You really do like one movie over the other. You're not wrong to like it, right? There's no ground truth to uncover. The voting process merely comes to a compromise of sorts. Right? So the way to formalize this would be, we could say that there are M alternatives. So here M is greater than 2, right? M could be 2, in which is not very interesting, but M is frequently greater than 2. You can think of these as the candidates or the outcomes or whatever options you have on the table. Voters have some preference over these alternatives, right? They prefer some over the other. Voters will cast the ballots based on those preferences, right? So, and voters will take these ballots, or sorry, there's some voting function that will aggregate these ballots and select a winner. Right? Fairly straightforward. Let's see what the results are. So here we have, no, that's Contagion. That's actually kind of surprising. And a lot of people want Transformers. Yeah, okay.
Star Wars.
Star Wars, yeah, Star Wars wins out. So let's for a moment, let's pause this. So right now the winning option is Star Wars, and Arrival is in second. So we'll turn this off. Somebody changed the vote in the last minute. Let's suppose we remove one of the options. Maybe Transformers is not available for whatever reason. I actually thought Transformers would be the least liked one because Rotten Tomatoes told me so, but that's apparently not a good guess. So let's run this second poll, right? So all I've done is remove Transformers. So we're gonna see what happens here. So I'm gonna vote again. So we have this set of 4 alternatives, right? It's slightly different icons, but so you have 4 movies that you're choosing over. And internally, what you might be thinking is, I have some degree of happiness I associate with watching this movie at movie night, or at least seeing it picked for movie night. Right? You could call that your utility. That's just a score of how happy you would be with that outcome. So here we have a bunch of utility values sort of painted onto these particular movies at the top. And then you might think, okay, now I need to submit a ballot. Right? It's what's called plurality ballot. We're not going to go into different voting systems, although we could have. We're going to formulate your ballot. And so what do you write on your ballot? Right? So you write on your ballot, you check off, well, your favorite choice. Right? Surely that's exactly what you do. Right? That's exactly what you do. You would vote honestly. Right? So let's see if that's actually what's happening here. Right? So we'll pause this. So we see that, okay, so most of you have voted honestly, I think, right? I'm just inferring from the way the pattern, most of you have actually voted honestly. There's a number of you who have jumped from transformers, right, to one of these two other options. But I wonder if any of you looked at this and said, well, my choice, if you didn't choose Rogue One, if you weren't a Star Wars fan, said, my choice wasn't going to win anyway, so I'm going to vote for something else. So a quick show of hands, that's something that you thought about doing, even if you did not actually do. Like one, maybe two. Yeah. So like that is a thought, right? That is a thing you can do. And that is exactly what subjective voting enables, and it's called strategic voting. So here we have the scenario that we just played out, right? We have, you are, let's say, the red agent here, right? And so obviously your favorite would be Star Trek amongst this particular list, right? And so everybody's, you're deciding what movie to watch. We have 5 people, each of you submit your choices, and here are in manual. So, and then you might think to yourself, okay, I really wanted Star Wars, but Iron Man is my least favorite movie. And so I'm going to change my votes. Right? Instead of saying I like Star Trek, I might say, well, I changed my mind. I'm going to vote Star Wars instead. And maybe by tie breaking, this actually changes the winning. And of course, other people can do this too. Right? Other people can say, oh, okay, I also don't like this movie that's chosen. I too will change my choice. And lead to a different outcome. This is called iterative voting. Right? And this idea could be scaled up. We could think about scaling up to a much larger. So here we have a very small example. We could think about scaling up to an entire social network. And yeah, question.
Just to make sure I understand, I'm assuming that people can change the votes after the result has been shown.
Yes. So yes, yeah. So I've hidden away a little bit of the math and the specific process, but the iterative voting process actually says we just conduct successive rounds of votes until nobody changes their mind. Yeah. But you could also think of the rounds as being like you're just feeling out what people are thinking, right? They could be they could be polls in the sense that they're polls conducted prior to an election. So we have what happens when you scale this up to a social network. In this case, you might not know what's happening in the entire network. You might have to guess. You have to build some mental model of what is happening. And so you might think, okay, so I am in a social network, or I'm in a community. There are N other voters in this community. All I know is that my friends are going to vote according to these particular colors. Right? 2 of them will vote orange, 2 of them will vote green, and 1 of them will vote blue. With no other information in mind, the only thing you could really think about is, well, what if everyone else in this community votes the same way? Right? And they're going to roll the die, and it's going to be a 5-sided die. 2 out of the 5 times they will do orange, 2 out of the 5 times they will vote green, and so on and so forth. And now I have a way in which I can think about what are the likely outcomes of the election. Right? And in particular, if you are a rational voter, the thing that you think about is, well, what is the probability that I will affect this election? What is the probability that I will cast a pivotal vote? In fact, if you're a completely rational economic voter, right, this is the only thing you care about. The only thing you care about is what is the probability that you will be able to cast a single ballot that tilts the election in your favor? Right? What are the most likely ties that you are able to break? And how would you vote to break those in your favor? That is the only thing you worry about. This is called being the pivotal voter. What is the probability that you will be the pivotal voter? And you can actually compute this, right? Because we've made this assumption that each voter votes according to a probability distribution. There are N of them. Each of them are rolling the same die. This is actually what's called a multinomial distribution. You crunch this crazy expression here, and you can actually compute the tie probabilities between every pair of outcomes, exactly how often that would occur. And then you can multiply that through by how profitable you can vote in whichever way to break those ties to get expected utilities. You do a bunch of math, and then you come to a conclusion of how exactly you would be able to vote to maximize the outcome of the election for you. And so what if everyone also performed this computation? Right, this is the assumption that we've made in one of our papers. We're in a social network. Everyone is sort of crunching the number this way. The social network might be set up in different ways, as we'll see in a moment. But what's happening here is, well, we can analyze this group of strategic voters of whether they are able to strategically come to a better outcome than if they just voted naively, right? They voted honestly, whatever their top preference was. And what we find is that as the social network gets more dense, right, in the sense that each voter on average knows more people, we find that people tend to strategize more, at least they tend to vote insincerely more often if they're allowed to do that. And more than that, as they're voting insincerely, or as they're voting more strategically, the average happiness of the outcome actually goes up. Right? That by exercising strategic voting, the outcome that is selected by this community is actually better on average for everyone. Obviously, sometimes they're going to select an outcome that an agent doesn't want, but on average, they're actually selecting better outcomes than if they were to not strategize. You can't quite read this off this because there's a lot of definitions that I've left out on exactly what is being drawn here. But the idea here is this blue line, the higher it is, the better it is to strategize over voting truthfully. Right? So I've sort of hidden away how the social network's actually set up. There's a bunch of algorithms that we use. One of the factors that we take into account is this idea of homophily. Right? This homophily is just this way of describing people who are alike tend to aggregate together. You think about who you talk to, right? The last 10 people you messaged on Instagram, the last 10 people you talked to on Discord, they probably share a lot of characteristics with you, probably similar age group, education, interests, right, etc. And so this idea of homophily presents itself in a lot of networks, and we incorporated this into our simulations. And one of the things that we find is, just go back here, the homophily networks are the ones in dot. We see that when there's homophily, when you're surrounded by people who think like you, there's less strategization and there's less good outcomes being selected as a result of that. When there's homophily in your network, there's less strategic voting. People are generally less happy with the outcomes that are picked, averaged over the entire population. And what is happening? Well, what's happening when there's homophily is you might be this agent down here, and you might see your friends, 2 out of the 5 of them are orange, and 2 out of the 5 of them are green. And you might think, okay, well, green is pretty good, I'll just choose green. But because there is homophily, this might be the world you actually live in. You don't know it. Right? Because you've surrounded with people, presumably you like green, and so you surrounded yourself with people who like green, or more than the normal population. But in actuality, in the population, the race is between the orange and blues. Right? And by casting your green ballot, which you thought was a good ballot to submit because of the information you have, you've effectively lost the ability to decide between the 2 real contenders of the election. And so the sort of high-level conclusions from this study that we did was that strategic voting can actually be a good thing. We think of like being insincere as being a bad thing, but from a utilitarian standpoint, right, from a utility standpoint, strategic voting can actually be a good thing for you, and it can help improve overall happiness. And homophily in networks actually causes the formation of these echo chambers. We started using this term. This paper was published 2016, but was written in 2015 because it takes about a year to get through. And so it leads to the formation of these echo chambers, which is exactly what we see, right, in the elections. And it hides the need for strategic voting, and it decreases overall happiness of the entire population, again, on average. Okay. So that sort of addresses 2 different ways of thinking about voting: epistemic voting or subjective voting. Another thing I want to address is that poll at the start, right? We had 8 people vote, and we have like 20-some people in the room. Right? How many of you abstained from voting in these polls? Why did you not vote? It's so easy. Just take a picture and then you hit skip because we don't really care about who was here. We're not taking attendance. And you can vote. Right? Why is it that we didn't vote? And this is a very real problem, right? The voter turnout in Canada is about 70%, which is pretty good, but not as good as it could be. Right? So what costs are there? There are real costs associated with voting. You need to think about what the issues that you care about are, which takes energy and time. You need to research what the positions of the different candidates were. When I was voting for the Ottawa election, I was trying to figure out who these people were, some of which have no web pages. That was actually, I guess it was easy to eliminate them because I couldn't find any information on them, but it takes time, right? You need to travel to and from the polling station, right? Which if in the most important elections are still in person, right? You still have to go to them, unless you thought ahead of time and sent it in by mail, right? And you got to stand in line for 1 to 100 minutes, right? My actual data points here, I've done both the 1 and the 100. So voting is really costly, and maybe it's intentional. Right? This is a political science discussion I won't get into, but it could actually be by design that it's costly. But the fact is, it is costly, and we just said you have to grind this number, and you have to be thinking about how likely are you going to be the pivotal voter, because that's the only thing that really, really matters, at least if you're a rational economic agent. Right? That the chance of casting this pivotal ballot is actually very small, especially in a large election. Right? And maybe you don't actually care about the issue very much. The benefits of voting is actually very small compared to the very real cost. This is the paradox of voting. Right? And so why would you vote? In some countries, it's a legal requirement. Right? When they have an election, they want all their citizens to vote. Many countries do this. Not many, but there's definitely a large list of these. For example, Australia, Belgium, Singapore. You might vote not because you necessarily think you will sway the election. It might be an expression of your beliefs, right? So you get some utility, get some happiness over filling out that ballot. And yeah, I did it. I did the voting thing. It might be a sense of duty. Or you might be like, yes, I did my due diligence. Right? It might be this sort of Kant's categorical imperative, right? That if nobody voted, then the world will be a bad place, democracy would fall apart. So we should do our duty in that very specific sense and do it. So there are other reasons, external reasons to vote. But is there a better way? Is there a better way to deal with this abstention, this costliness of voting? And this is where liquid democracy comes in, right? We have this idea that one person, one vote, right? Each person has one vote. But what if I could take my ballot and just give it to my friend, right? Like I don't have the time to vote. I don't really care so much. Right? Maybe I trust Forrest with my vote. So here you go. Right? Maybe we have ideological beliefs that align, at least roughly. Right? So what if this delegation was transitive? Right? Transitive in the sense that Forrest might say, maybe this is not also something you care very much about. Maybe you also hand these ballots, both of them now, off to a third person. This is not such a strange idea. Right? So we have direct democracy, which you practice in ancient Athens, for example, where everyone says, I vote, right? And every single vote from everyone is counted. It's a little bit harder to do in a larger society, possibly doable, right, with the internet. We have what we now have is representative democracy, right, where we say, well, we've selected some kind of representative from our group. They will vote in lieu of us. We don't actually vote on the decisions that take place in the government usually. So we already, in some sense, delegate our voting power to someone else. We also practice sometimes in proxy voting. So I was in a homeowners association because of the place where I lived in. They had like a little fancy pool in the back, tiny pool. And there was like questions every year of like, where should they invest their $600 in maintenance or whatnot. And so there would be a person who would come by my door and said, well, if you're not planning to vote, can you let me have your vote? Can I be your proxy? And you can fill out a form that says this person can be your proxy. They will have your vote instead. And so you can delegate, right? So here we have one person that's delegated this person has 2 votes, this person has 3 votes, right? You get one from yourself, obviously. Right? And so if we just allow these delegations to chain, we have a delegation chain, we have what's called liquid democracy. Right? This idea that you can have multiple people chain their delegations to an eventual voter. Right? So this is not such a sort of strange issue. We can think about what this might look like. So let's say we have some issue that we care about, and voters are arrayed sort of on this interval, right, from 0 to 1 based on the strength of their position or the preference for a particular issue. You could frequently think of this as sort of the left and right of the political spectrum. Right? And the voters or citizens rather, are located on this interval based on what their preference is. Right? And so voters on top. So citizens are arrayed at the bottom, and voters are arrayed at top. And the voters, we call them voters because they're the people who actually care enough to go vote, let's say. Right? They care enough about these issues that they want to go vote. And they have certain, so this is just indicates their position along this line. And the general citizens have preferences too, but they don't actually care enough to go vote if they were required to do so. Right? And so citizens are allowed to then delegate their vote to whoever they want. Of course, they will delegate it to the closest person who wants to vote. Right? So let's first consider what happens if we have no special system. It's a direct democracy in the sense that only the voters, this top row of voters, will go vote because they're the only ones who will bother to do so. And let's say, so citizens will abstain. And so the winner, let's say, is the median voter, is the middlemost voter. And so we can choose the middlemost voter here. So that the result is 0.6 right along this scale. But we can also calculate the true median. Right? The true median in this case is just left of 0.5. Right? And this is in some sense the real answer to the question, because everyone has one vote, even if some people didn't bother to submit it. Right? In the general population, the actual result should be here, whereas the median of the voters in this example is off to the right. Right? And now we can think about what happens when we allow people to delegate. Right? So we've concentrated some more voting power here on the left. Right? These 4 people delegate to this voter who has now 5 votes, and so on and so forth. The median of voters before was over here at 0.6. But now you can calculate, you can do some sort of counting on your fingers, right? You can see that the weighted median is now shifted to this voter here on the left, which we see, at least in this example, is closer to the true median. And so is this always the case? Because I just cooked up that example. Maybe that's only works for that example. And the result is actually quite promising. There's a theorem that says this is always the case, no matter the distribution of the voters. Right? And this is true of any distribution. We had a discrete example, but the distribution could be continuous distribution. There could also be any number of voters, including infinite number of voters, right? We have truly continuous distribution. And we'll do a quick proof of that. Right? So here we have, we can in fact show something a little bit stronger, that the weighted median is always the best, always chooses the best representative, right? It always chooses the voter that is going to be closest to the true median. Right? So, and of course, that would be the best voter to pick. So here, let's say we have a bunch of voters, right, that have presented themselves. We have some distribution of the general population, right, in just some kind of curve. And we can say, we can find the median. There exists something that is the median in this population, right? Or the mean, if you will. That's the easier way to think about this. Right? So it's probably around here. I just kind of eyeballed this. But the median means half of the voting weight is on the left, right? And half of the voting weight is on the right. And so if you think about what this means is when they delegate, everyone who's sort of on the left here will delegate to a voter that's on the left. And there's a midpoint between these 2 voters. So midpoint here that splits the delegations. And the midpoint's always on the other side of the true median. And so the voter that is selected as being the weighted median voter is always going to be the one that is closer to the true median. Geometric argument in the sense that I could try to explain it again, but I would just say the same words. You kind of have to draw the picture yourself and kind of convince yourself that this is the right answer. So that's very promising. There are some other benefits to liquid democracy as well. right? So that each citizen gets to choose for themselves whether or not they will become a delegate. In sort of the ideal form, they could become a delegate, or sorry, you could become an active voter, or you could delegate your vote. You can choose by issue in sort of the ideal form of this liquid democracy. Right? It's a low barrier of participation. If you didn't really care about an issue, you could just delegate your vote to someone who you kind of trust or you vaguely align on this kind of issue. And there's accountability, right? Somebody who's chosen as a delegate only has as much power as is delegated to them. If they start misbehaving, if they start doing things that are not in the interest of people who delegated, well, they can just change the delegation to someone else. You can always go back and just vote yourself. You can't go back in time, but you can always just stop delegating and you can just vote yourself if you're not happy with how the results got. There are, however, some issues. Right? As with all things, there are always some issues. It becomes kind of a popularity contest, right? It gives you this artificial mechanism for concentrating power. That's already a problem in today's democracy. Would this make it worse, right? And there's concentration of power in people who are socially influential or politically influential, with people who want to be convincing. Right? So that might not be a good thing. If you make this assumption of epistemic voting, right, it's a very strong assumption that we're trying to uncover the correct choice. Well, it turns out that, well, it's maybe obviously that it is worse than if everyone was voting, right? Because that's not the benefit of the system that's giving you more accuracy. It's just making more people vote easier. However, there are some issues where some very carefully constructed examples where it's actually beneficial to delegate to someone who is lower skilled than you, which is kind of paradoxical, that delegating to a lower skilled expert actually improves the overall predictive power of the aggregate result, which is a little bit weird. I'm not going to go into that example or these examples because they're very carefully constructed, but it's something to keep in mind. A more interesting thing to think about is, well, experimentally, can we actually do this? Can we know when to delegate and who to delegate to? And there's been a line of research from MIT that looks at exactly this question. There's a bunch of experiments where participants are going into a lab and they get to answer a question, like a series of questions. They're given a category and they say, would you like to delegate this to someone else? And if you said yes, you still answer the questions anyway, because this is what counterfactual means, right? They want to construct the what if, right? Counterfactual means what if. And so we can see whether or not their delegation would have been a good idea. And what we see is, so this is a example of what they would see. Right? So here you will be asked now to identify a location of a landmark based on an image. Right? And you can choose whether or not you think it's a good idea to delegate. And then you would be asked the question anyway. So here we have an image. The question is this in France? And I honestly have no idea. I honestly have no idea whether this is in France. Probably not. I don't know. Low confidence for me. Right. Maybe some of you have special insight. So what were the results? Because they can look at this data and see if people delegated successfully. Right? And what they found was, yes, for the most part, people who were low skill, right, before they didn't get to see the question before they were asked to delegate, they were successfully able to identify categories of questions where they were low skill and delegate them. For the most part, they delegated to people of higher skill. However, they had a very small sample size. So these results I just said are not statistically significant, but they are promising. So there's more research being done in this direction. Okay, so I'm going to breeze through sort of this last section, which is quite a bit longer. One of the central aspects of democracies is allocating resources. Right? In fact, one might say that politics happens wherever people disagree on what to prioritize. Right? Whenever you have a disagreement over where resources go, that's where politics happens. And so is there a way for us to then, as computer scientists, come up with an algorithm that allocates resources fairly? And there's a lot of different, what does fairly even mean? Right? That's also a very big question. Can we define, because in order for us to optimize a criteria, we have to define it first. Right? And so this is a very large part of computational social choice, and it's divided into different categories, depending on what is it that you're dividing. You could be dividing what are called divisible goods, goods that can be chopped infinitely small, right? So land use rights, computational time, budget, for example. Right? And then, of course, there are indivisible goods, things that cannot be chopped apart. Right? For example, inheritances, we think about inheriting items, art objects, houses, organs. Right? Half of a kidney is not going to do anyone any good. And there's two variations of this as well. There is indivisible good with money, where you're allowed to pay each other for having taken a good, right? To sort of smooth things over. And of course, without money. And of course, without money, sometimes you might think, why not? Well, if you think about organ donation, well, there are laws that forbid exchanging money when there are donations of organs involved. You can't pay someone for their kidney, that's illegal. So it might not be appropriate to involve money. And today we'll explore this last one, and sometimes the most difficult of these. Right? So let's say you and your roommates are moving out, and you divide a bunch of common items amongst yourselves. Different people value different items to a different degree, and you might value some more than others. And see. And the way to do it is then you will be dividing. You want to partition the set of goods that you have. So here we've got an Apple computer, a bicycle, a camera, a dog. It might be a toy dog if you don't think it's appropriate to split a dog without asking for the dog's permission. An egg beater, because I ran out of things that start with E, a frying pan, and a guitar. And so the thing you want to do is you want to separate these into bundles and give each person a bundle of goods. You want to take all of these items, put them into bundles, and to do it in a fair way. Or there's that word again. What do we mean by fair? Well, one thing that you could do if you have two players is what's called the divide and choose algorithm. You take one player, player one will divide the items into two bundles, and player two takes whichever bundle she prefers. This is if you have any siblings, it's very likely you've been asked to do this with your siblings. It's in the Bible. That might be why that some parents know this algorithm. But here's an example. So player one is on the left. Right? Player one says, I will split these into these two bundles. Player one wants to split them into roughly equal bundles. And player two says, well, okay, I like this one better, so I'll take that one. And player one will take the other. Right? This is fair in the sense that player two always thinks she got the better bundle because she got to choose. And player one's a little bit in a stickier situation. Player one wants to minimize the difference between these two bundles. Ideally, player one wants to create two bundles that she would equally like to take. And without being able to do that, she wants to minimize the difference because she could always get stuck with the worst of the two bundles. Right? And so in some sense, she, in the worst case, loses out the smallest possible amount. She's engineered it so that she would lose the smallest possible amount in the worst case. And this is what's called the minimax share. Right? This is the amount that a player, if they were forced to divide the bundles and then take the worst bundle, what is the amount of happiness they can guarantee themselves by doing it that way, right? It's the dividing it into bundles and what is the value of the worst bundle for them. And so ideally, we want an algorithm that can guarantee the MMS value for each player. And in two players, the divide and choose does exactly that. It's about as good as it gets. So the question is, what about three players? Right? Can we generalize the MFS value for three players? And we can. We can say, this is, if you were to choose three divided into three bundles, your MMS value is the value of the lowest bundle. Right? So how do we extend divide and choose into three players? And if you're from my multi-agent systems class, you might think, yes, I know this, because there's some crazy thing you can do back and forth where you cut, it's called cake cutting. When it's continuous, you cut the cake and you cut it again, and you cut it into little pieces and you shuffle the pieces around. We can't. In the indivisible goods case, you can't cut things into tiny pieces and shuffle them around. And so you cannot actually extend the divide and choose algorithm into 3+ players. In fact, the MMS value cannot be guaranteed. There are counterexamples where you cannot guarantee them for a 3-player case. Right? So we have to have another notion of fairness, right? And another notion of fairness is envy-freeness, right? Envy, if you have siblings, you understand this feeling very well, right? that other person got the thing I wanted. I wish to have that instead. I want that bundle instead. And that's exactly this idea of envy. A player envies another player if they would prefer to have that person's bundle instead. And envy-free, an allocation of bundles is envy-free if no player envies another player. And the question is, can we always obtain an envy-free allocation for at least two players? Let's start with that one, because this is a new definition. And the answer is no. The answer is no. And the counterexample is trivial, where you only have one thing. And so player one maybe gets to divide, and player two gets to choose, and player two takes it, and player one is not very happy. It's definitely envious. So can we approximately be envy-free? Right? Can we approximately be envy? Can we get as close as we can get? Maybe we're off by one, right? We're off by one. And so that leads to this idea of envy-free up to one good, right? That no player is envious of another person's bundle if one of those items in that bundle gets destroyed in the process of transferring it to you. And here we define it as the most valuable item from that bundle is removed. That's envy-free up to one good. So we have this example again. Is this envy-free up to one good? Yes, it is, because there's only one good. And so player one is maybe not thrilled about this, but it's a reasonable definition, and in some sense as good as it gets. Right? We can't, it's not quite true. There's a better definition, but we won't get into it. It's very technical. So we have this idea of envy-free up to one good. Do algorithms satisfy it? And if we have three players and you're asked to choose between something, and if you have moved out with exactly that scenario, you probably did this, you do round robin, right? If you've done sports teams picking, right, back in phys ed class, right, you've probably done some version of this. Each person takes turns and picks their favorite thing. Right? And it turns out this very simple algorithm, round robin, is EF1. It's envy-free up to one good. And we can prove it. The easiest way to prove this is to divide your picking, you write out your picking sequence and you think of it as proceeding in different phases. So here we have red goes first, then green, then blue, and then red again, and so on. Every time a person goes, you think of a phase until they go again. And surely within this phase, this player green here is envy-free with this particular, within these three items that were allocated, because clearly green picked the best of the remaining items. So green would prefer to have the camera over the dog or the bike, right? And so on and so forth. So they're completely envy-free within these phases, and there's only at most one item for each player left over. Therefore, EF1. And you can show that for the blue player, that is also the case. And obviously the red player got to pick first, and so they are also envy-free. They're in fact envy-free, not even EF1. So this works for additive valuations where you can add the values of these objects together. But there is a more complex version of this, right? They can't capture the idea that some items work well together and other ones do not. So for example, maybe you would like to have the egg beater and the frying pan because you like cooking, but maybe your Apple computer doesn't work well with the camera and so you don't want them together. It's worth less to you if you got them together. We might agree that at least all items are valuable to some degree, that getting an item is better than not getting an item. This is what's called monotonic valuations, right? The same concept as monotonic functions, but for sets. And so the theorem here is that the question here is, can we get EF1 from monotonic valuations? And the answer is yes, we can always do this, and we can do it in polynomial time, which is kind of uncommon for social choice. Right? And we'll do very quickly, we'll just do the overview for this algorithm, right? The idea is that we will partially we'll allocate these items one at a time. Every time we allocate, the partial allocation will be EF1, and we'll construct an NV graph that we'll use to allocate the next item. Right? We'll allocate these one at a time. And so the way we generate an NV graph is that we simply construct a directed graph where we draw an edge from I to j if I envies j. Right? So here we have green envies the person with the bike, because they would rather have the bike rather than the frying pan, probably understandable. Red here also envies the other player because they would rather have the bike than the egg beater. And we need to use a lemma. Right? The lemma basically says if I have a cycle in my NV graph, I can decycle it in polynomial time. And this is actually pretty straightforward to see, right? Here we have a cycle with a much more complicated graph now. These are bags because they're bundles and not actual individual goods. Right? If there is a cycle, that means there's a group of players who are all saying, I would like the next person's bundle. And so the easiest thing is we'll just have it then, right? We can just let you have the next person's bundle, right? And untangle this cycle. It might cause, and it will cause these other edges to shift, right? Both of these players want the paper bag. And so they still want the paper bag, even though a different player has it now. And equipped with that, I'll just outline the algorithm rather than running through it. Right? And you start with an empty allocation. You allocate the first item randomly, whoever, it doesn't matter who gets it. And then now you go into this loop. At the start of the loop, you will be EF1, and it will be cycle-free because you will allocate the item to a player that is not envied by anyone. In some sense, like the worst off player will get one more item. And this will still be EF1, because nobody was envying that player anyway, and they received one more good. So some people might envy that player now, but it's only up to one good. Right? It might generate some cycles, but then you apply the decycling lemma, and you remove that cycle. Right? And you just keep repeating this and allocate all of those items. So I'm cautious of time, so instead of running through the algorithm, I'm just going to sort of skip to the end here. This algorithm is a more complicated version of the previous algorithm. The reason why is because we're using this monotonic valuation. And so there are other applications of fair division. It would be used for assigning internships or housing. It could be used for what's called participatory budgeting, right? This idea that a community has a certain amount of budget to work with, and they have to vote on the projects that they want to go ahead within this budget. There is rent division, classic problem for students, right? Who gets to pay how much of the rents? Because the rooms are of different sizes. We go over that particular one in one of my courses. And there are all sorts of scheduling problems that have fairness issues associated with them. Okay. If you're interested in trying out algorithms that actually split rent, for example, or divide fair or divide items, there's actually a site that's produced by our community called splitit.org. And that implements a lot of these algorithms in a way that explains to you why a certain allocation was sort of put into place. So I was going to talk about information propagation very briefly, but I'm going to skip that section and just sort of go to the end. Right. So what can we do about the state of democracy? Right, it's a very big problem, and there are many interesting questions to ask and many interesting questions to work on. Computational social choice gives us a lot of computational tools, right? It gives us a lot of ways of solving these, and these tools can help form part of a solution to this very big problem. But there is a great need for interdisciplinary collaboration. We can only take it so far using only computer science techniques. At some point, we need real-world data, we need real-world experts, people who are knowledgeable about the specific domains that these things take in. And so this is sort of a overall view of very narrow slices of multi-agent systems, computational social choice. So a little bit of game theory and social networks in there. And one way to think about what I do is that I am reasoning about reasoning systems that reason about each other. It may be kind of a mouthful, but hopefully you have a little bit of idea of what exactly that is. These are just some of the wonderful students that I work with, the ones that sent me pictures. And if you are interested to learn more about this, I teach the multi-agent systems course, which has not this content, but content like it. I'm doing this next fall. I'll also teach the ethics course in fall. And I'll also be teaching social networking again next winter. So, thank you.
All right, thank you, Professor Sang. That was an amazing presentation. We had originally planned to do a Q&A session with like a proper mic. However, it seems the one approach that I think we can take that we discussed over chat just now was that we can actually temporarily, when someone in the crowd wants to ask a question, flip the microphone of the room on so that the room sound is broadcasted to the stream. So Forrest, do you think that would be okay?
Yeah.
Okay, cool. So does anybody have any questions? Forrest.
So one point that you discussed, and I don't know how to pronounce it properly, but homophily, is that correct?
Mhm.
Okay, so you described this idea that homophily sort of like dictates how, what results we get when we vote based on how close we are together as a group. And so what I'm sort of interested in is how do these ideas apply to stuff like when we're working on like tech teams or stuff that's in like small, like if I'm working on a team of 5 people, we discuss an idea, try to figure out what's best to do. Does this idea apply to that as well?
So there's an interesting relationship that I recently came across where there are studies, I wish I have like a citation in mind, but there are studies of like how teams should work better together within a large organization. And one of their recommendations is that teams that are far across the organization should talk to each other more often. Because frequently you get into a situation where a team is working on something and they really only think about it in one way. So frequently in engineering firms, right, when they're building like a plane, they're designing this particular system, designing a particular way, when maybe another part of the company are like, well, that's not what we need at all, and you're just designing this crazy thing nobody will use. And so that is like one of the organizational management issues that they encourage teams to talk to other teams that are far away in the company. Not sure if it's necessarily because of this homophily situation. It's more of a small world network issue where you want to reduce the distance it takes for information to travel from one part of your company to another. So hopefully that addresses that point a little bit.
But if we manage to reduce the distance, just assume that everyone has all the information about a product or a company or a government, whatever, then how could we, or what would be the next steps there to really make a society better by implementing technology?
Yeah, so one of the issues is it's a very big problem, and we can only really solve small parts of it at a time. And hopefully once those parts are addressed, we can solve other parts and maybe work on larger parts of the problem. Yeah, it's maybe not the most satisfying answer to have, because we'd like to be able to say we have a solution and it's big and will change the world. But unfortunately, we have to start with sort of the grassroots versions of these, right? Can we make this one thing fairer? Can we make this other thing a little bit better, and work from there?
Does any country, or do we know if there's any country or has been any country that has actually practiced a liquefied democracy?
Excellent question. So the liquid democracy is actually practiced. It sort of had its heyday in the 2010s, mid 2010s. The German Pirate Party, sort of the big story. They were reasonably powerful in parliament for a while. They've since they still have 1 seat, but they were run entirely on a liquid democracy platform. So they were kind of the big story. There was attempts in, I think, Australia, in Argentina. I forget the other one. Maybe, I think it's Australia, where they tried to, so there were politicians who were running on the platform that they would run a liquid democracy process and they would just do whatever that process gave them. And they would just vote accordingly based on that process. It was sort of a way to like patch it into an existing democratic process. However, none of them actually won. Yeah.
I actually have something that is kind of, I don't know if it's like an answer to your question, but this liquid democracy talk, I don't know if this is democracy, it's kind of a little bit different, but it's similar in concept. So Czechoslovakia in like 1989, 1990, they kind of broke up from socialism, so it kind of was transitioning to a democracy. And I think they were like all the state-owned companies, they were like giving all the people like these shares. But it's like if you have this share, you can like choose to like kind of own a company or from it or something like that, and you could transfer them to other people. So then there are some people who would like make deals like, hey, I'll give you some money in exchange for those shares, and then the people who don't know say, oh sure, yeah, I don't care about this thing, you can have it, you can vote with this. So it kind of reminded me of like the people who don't feel like voting, and then these people, they can use all these shares to suddenly like, oh, now we suddenly own 60% of this factory, or now we own the factory, now we're the shareholders, now we can make all the decisions. So it's like it actually happened. So it's
That's
maybe
yeah.
think about that.
That's an interesting, like, I'm already thinking like kind of run a simulation on that, right? Like what are the assumptions that would lead to that kind of systems, and is it just a pointless system to have because no version of that works, or could a better version of that be implemented? Yeah, it's a good point. Thank you.
I think another thing I just realized is that like it almost like the only reason why this happened is because of the transition from kind of communism, where the state owns everything. Nobody's allowed to own any piece of property. To, oh well, we have all this property and now we want people to own it. So here, have this thing. So it's almost like it's like kind of like artificial in a way, in the sense that it's like because of the transition from like communism to democracy. It would never happen in a democracy otherwise, because nobody would be like, oh, now you can easily own this company. I don't know.
Yeah, there's definitely a people issue here, right? That we're ill-equipped to discuss as computer scientists, right? Like a political scientist or a sociologist. Or this is the importance of having an interdisciplinary team. Right? They would be more well-positioned to comment on, well, this is why people acted this way based on their upbringing or the society that they grew up in. Yeah.
So, there's a thing about the voting, changing the rules, right? Voting in order to voting because you know that your decision is not going to win, so you vote for your second best or your third best choices. And so, growing up in Mexico, when you voted for a president, that was the norm. You never think that your guy is going to win. You just you rally up the one that at least was. So using an example that is relevant, thinking about Trump in the U.S. and was it Clinton? Trump or Clinton? So there you have what many people would have said, and I'm not judging anyone, but many people would have said that these two choices were bad choices. They were some of the worst reported proposals in the United States. So when we think about, and of course you don't know that result when you vote for a president, you do it once and that's it, so it's not even guesswork. But how can we avoid this? Do we know how we can avoid the idea of, if we're not voting for the best, then eventually we're going to get options that are neither one of them is a good option. We're just choosing a good option, which is the least worst.
So that's a really good question. It's very broad. So one version of that question that could plausibly be answered is the primary system in the US where you have like the Democrats have an election and they choose their candidate, and the Republicans have their election and they choose their candidate, and then they have an election with these two candidates and whoever heck else wants to run as independent. Is that a good system? Does it lead to weird incentives, right? Does it lead to some kind of weird corner case that maybe the real world is trapped in, right? So that's one version of the question. Is the primary system from a computational standpoint, from a mathematical standpoint, is it not a good system to employ? Another version of that question would be, thought of a thing, but it escaped my mind. Yeah, think about that for a moment. Escaped my mind. What the other thing I was going to say? Yeah, we'll have to move to the next question to think about what. Yeah.
I have a question about monopoly. What do you think actually have person shares some interests and we're talking about the outcome, certain about the right outcome, or they just know that particular vote will win, and they just, like, let's say it's the leader of the group, influences others, and because we share interests, we basically something delegate their roles to this person, like in a sense.
Yeah, so in the system, there is no other process happening. It's just that the social network is wired in such a way that people who have common preferences tend to be networked together. And what's happening is that when they survey the landscape and think about what is happening elsewhere in the network, they see so many of their friends that have the same opinion. They think, oh, my opinion must also be shared widely in the network, and therefore I will vote a certain way. Usually whatever is my favorite, it seems to be a strong contender amongst my friends, and so I will vote for it.
So it sort of like increases their confidence level in outcome, right? So
It skews what they think the likely outcomes are.
So is there something which changes when you have a smaller population versus the larger population?
Yeah, that's a good question. I don't remember we ran that experiment. I think we ran it, but we didn't actually write it in the paper. That when we ran it on smaller ones and larger ones, the general trends are the same. Yeah. There are structural issues with the graph generation process that might not scale well, but that's a very under the hood kind of thing. But in the real world, right, we would expect that homophily plays a very strong role at any size of a population larger than maybe this classroom.
Thank you for your talk. And as you know, the concepts of this are actually votes by consumers about how likely they like that thing or want that thing. I don't know, is there any connection between your studies and
Probably. So one of the sort of places where I draw literature from, when literature's a site, is economic game theory, right, where this exact thing happens. Is not. I can see the parallel with voting, but usually those literature is separate. But certainly this idea of it's definitely a multi-agent system where they're interacting and they're determining prices.
okay. Another question was I didn't really get the relationship between the strategic voting and ethics about results.
Yeah, so what we see in that simulation is that under those particular assumptions, when there's more strategic voting behavior, when people are allowed to be strategic, happiness generally goes up in terms of the outcome being selected.
So is that like a result that you observe? Is there a reason behind it?
Yeah, so one of the ways to think about it is that if you're not voting strategically, you might, in a multi-candidate election, really, if you're not voting for either the winner or the runner-up, your vote is lost. Right? There's no point in voting for a lower down candidate because it didn't matter. If you had voted for the runner-up, at least you were really yelling into the wind there, saying this person should win, but other people yelled harder. But if you were voting for number 3, then that person was lost either way. And that's exactly, I think, the dynamic that happens where if you were voting non-strategically and you were voting for number 3, then your voice was lost effectively, even though you could have helped determine who was number 1.
I think we'll put up questions here in the effort of time. So everybody